Hello friends, welcome you all to the 33rd lecture on functional analysis and its applications. In this lecture, we will discuss the weak convergence and strong convergence. These are the contents of today's lecture. Completion of inner product space, strong convergence and weak convergence. Completion of inner product space. Proposition. Let xn and yn are two Cauchy sequences in inner product space X. Then the scalar sequence Zn, that is Zn is inner product of xn, yn, is convergent. Proof. Let us show that Zn forms a Cauchy sequence in F, where F is either C or R. Now we can write Zm minus Zn. M and n are positive integer. Here Zn define inner product of xn, yn. That is Zm minus Zn can be written as inner product of xm, ym minus inner product of xn, yn. Here we added inner product of xm, yn and subtracted inner product of xm, yn. Then we have this. From these two terms and another these two terms, we can write by using the fourth property of inner product. Then these two terms, that is inner product of xm and ym minus yn, and these two can be written as inner product of xm minus xn, yn. Here yn. So Zm minus Zn is this one. By using the triangle inequality, we have this one, and now using the Schwarz inequality. Okay, taking the modulus of both sides. So this is mod of Zm minus Zn less or equal to mod of first term plus mod of second term. So using the Schwarz inequality, this is less or equal to norm of xm into norm of ym minus yn plus this norm of xm minus xn into norm of yn. Since every Cauchy sequence in metric or normed linear space is bounded, there exist two constants C1 and C2 are positive such that norm xn less or equal to C1 and norm yn less or equal to C2. So therefore C is maximum of C1 and C2. We have mod Zm minus Zn less or equal to C into norm of ym minus yn plus norm of xm minus xn. In view of the assumption that xn and yn are Cauchy sequence, so we conclude that Zn is a Cauchy sequence in the complete space F. That is, this is tend to 0, this is also tend to 0. Okay, so that mod of Zm minus Zn tend to 0. So that the sequence Zn is convergent. That is limit n tend to infinity xn yn exists. Okay, strong and weak convergence. So far we have dealt with convergence in the norm or strong convergence in the norm linear space. In this lecture we shall introduce a new type of convergence called weak convergence. Strong convergence of sequence. A sequence xn of vectors in normed linear space n is said to converge strongly to a vector x belonging to n if norm of xn minus x tend to 0 as n tend to infinity. Okay, this is known as strong convergence. Okay, weak convergence of sequence. Let xn be a sequence in normed linear space n is said to converge weakly to x belonging to n if for every linear functional f belonging to n star f of xn converges to fx as n tend to infinity. This is also can be defined as for every epsilon greater than 0 there exists a natural number n0 such that mod of fxn minus fx less than epsilon for all n greater or equal to n0 and for all f belonging to n star. In this case, we write xn converges to x weakly. This is just notation for weakly convergence. Here x is called the weak limit of the sequence xn. Theorem. Let xn be a weakly convergent sequence in normed linear space n and let xn converge to x weakly in n, then first the weak limit of x of xn is unique. Second, every subsequence of xn converges weakly to x. Proof. By contradictory, we prove it. If the weak limit x of xn is not unique, let xn converges to x weakly and xn converges to y weakly. Then by the definition of the weak convergence, we have f of xn converges to fx and fxn converges to f of y for every f belonging to n star. Since fxn is a sequence of numbers, its limit is unique. Hence, fx is equal to fy, that is for every f belonging to n star we get fx minus fy equal to 0. This implies that f of x minus y equal to 0 because f is linear. Okay. If n is non-linear space and f0 a non-zero vector in n, then there exists a function f0 in n star such that f0 of x0 equal to norm of x0 and norm f0 is equal to 1. This one is norm f norm x minus y equal to 0. Okay, so here norm f is equal to 1, then norm x minus y is equal to 0. Therefore, norm of x minus y equal to 0 if and only if x is equal to y. Okay, hence we get x minus y is equal to 0, that x is equal to y. So here our assumption is wrong, that to limit x and y. Here x and y equal. Okay, this shows that the weak limit is unique. Second, since f of xn is convergent sequence of numbers, every subsequence f of xnk converges for every f belonging to n star and has the same limit as the sequence fxn. Thus, every subsequence of xn converges weakly to x. weak convergence in inner product space. A sequence action. Here we have discussed the weak convergence of sequence any function f belonging to n star. Suppose here in this case f is inner product. Okay. So weak convergence in inner product space is defined as follows. A sequence action of vectors in an inner product space X is called weakly convergent to a vector X belonging to X if inner product of action Y converges to inner product of XY. Here F is inner product. The condition in the above definition, this can also be stated as this one left side and using the force property of inner product, we get inner product of xn minus x y tend to 0 as n tend to infinity for all y belonging to x. Here x is inner product space. Okay. So it is convenient to reserve the notation xn converges to x for strong convergence and use this notation xn converges to x weakly as this for weak convergence. Okay. Theorem. First theorem. A strongly convergent sequence is weakly convergent to the same limit. That is, xn converges to x. This implies that xn converges to x weakly. Okay. Proof. Suppose the sequence xn converges strongly to x. This means norm xn minus x tend to 0 as n tend to infinity. By Schwarz inequality, modulus of the inner product of xn minus x y less or equal to norm of xn minus x into norm of y. Okay. Here given xn is strongly convergent, so norm of xn minus x tend to 0, this one tend to 0. Okay. It means total tend to 0 as n tend to infinity for all y belonging to x. That is, inner product of xn minus x y tend to 0. Okay. This is the modulus value. So this is tend to 0, that is inner product of xn minus x y tend to 0 as n tend to infinity. This proves the theorem. This is also can be written as xn converges to x weakly as n tend to infinity. Next theorem. If xn converges to x weakly and norm xn converges to norm x, then xn converges to x as n tend to infinity. It means if we have weakly convergent sequence, okay, and with condition norm xn converges to norm x, then sequence xn converges to x strongly. Proof. By the definition of weak convergence, we can write inner product of xn y converges to xy as n tend to infinity. So xn, xy all belonging to x. Hence, we replace y by x. Then inner product of xn x converges to inner product of xx. That is norm of x square. This is equation 1. Now, norm of xn minus x square, we have to prove this tend to 0, okay, for strong convergence. So now, square of the norm xn minus x equal to inner product of xn minus x, xn minus x, okay. we can expand it using the third and fourth property of inner product, that is inner product of xn minus inner product of xn x minus inner product of xn, here minus and minus plus inner product of xx. So this can be written as conjugate complex of the inner product of x and x. Okay, and also we know that inner product of xx equal to norm of x square. So inner product of xn xn can be written as norm of xn square, and this is as it is, and this one minus conjugate complex of inner product of x and x plus norm of x square. We know that z plus z bar is equal to 2 real part of z. So this is norm of xn square, and this one minus 2 real part of the inner product xn x plus norm x square. Okay. So this is given norm xn converges to norm x. So this is less or equal to norm x square, and this is inner product x and x converges to norm x square. So this one minus 2 norm x square plus norm x square. Okay. So norm x square plus norm x square, that is 2x square, and this is minus 2 norm x square. So cancelled out. Therefore norm of xn minus x square tend to 0. That is norm of xn minus x tend to 0 as n tend to infinity. Hence xn converges to x strongly. This completes the proof of the theorem. Next theorem. In a finite dimensional normed linear space n, the strong convergence and weak convergence are equivalent. Proof. Since strong convergence implies weak convergence in a normed linear space n, it is true also in finite dimensional normed linear space. So it is enough we prove that weak convergence implies strong convergence in finite dimensional normed linear space. We establish this with the help of the dual basis. Let xn converges to x0 weakly. Okay. So that f of xn converges to f of x0 for every f belonging to n star. If E1, E2 and so on Ek is the basis of n, let us take xn can be written as xn1 E1 plus xn2 E2 plus and so on xnk Ek, because here xn has n dimensional, that is xn is equal to xn1 xn2 and so on xnk. Okay. So xn can be written as this. Similarly, x0 also can be expressed as this, that is x0 is equal to x0 into E1 plus x0 into E2 plus and so on x0 into Ek. Since f of xn converges to f of x0 for every f belonging to n star, we can consider the convergence of the dual basis fj is subset of n star of ej in n. From the definition of the dual basis, we have Fj of Ei equal to 0 if I not equal to j, and equal to 1 if I equal to j. Then Fj of Xn, that is Fj of this right side. Okay. So using this property, we have Fj of Ej x nj. Okay. Value of this is x n1 Fj of E1 plus x n2 F of E2 and so on. That is, this can be written as x n1 Fj E1 plus x n2 Fj E2 plus and so on plus x n j Fj of Ej plus and so on x n k Fj of Ek. Okay. So using this property, if j and I equal, then Fj of Ei is equal to 1. If I not equal to j, that is 0. So from this, we have only one term Fj Ej is equal to 1. Okay, so we have only one term this Fj Ej into x and j, and Fj Ej is equal to 1, that is x and j. Okay. Similarly, we can express Fj of x0, this one. We have Fj of x0 is equal to x0j. Okay. Since Fj xn converges to Fj x0, we have xnj converges to x0j as n tend to infinity. Hence, norm of xn minus x0. Here we have xn and x0 is this. Okay. So, norm of xn minus x0 is equal to summation j is equal to 1 to k xnj minus x0j ej. Okay, we can write this is less or equal to, this is the norm. So norm inside the summation. So less or equal to summation j is equal to 1 to k norm of xnj minus x0j into ej. So this is as a scalar and ej as vector. So norm of alpha x is equal to mod alpha norm x. Okay. So norm Ej is equal to 1. So we have only this summation j is equal to 1 to k mod xnj minus x0 j. Okay. Since xnj converges to x0j, this, that is this one tend to 0. Here I think equal to, here equal to. Okay. So norm of xn minus x0 less or equal to this. Here less or equal to. So norm of xn minus x0 tend to 0 because mod of xnj minus x0j tend to 0 by this. Hence norm of xn minus x0 converges to 0 as n tend to infinity. We know that norm x is equal to 0 if and only if x is equal to 0. So norm of xn minus x0 tend to 0. Okay. If norm of xn minus x0 tend to 0, it means xn minus x0 tend to 0. That is, xn converges to x0. Here, it is converges to 0 under norm, that is, xn converges to x0 strongly. This completes the proof of theorem. In this lecture, we have discussed the completion of inner product space, weak and strong convergence with related theorems. These are the references which have been used in this lecture. Function analysis, Dover publications, written by George Beckman and Lawrence Naresi. Second, function analysis with applications, John Whaley, written by Erwin Krejcik. Third, function analysis, New Age International Publishers, written by B.V. Lemieux. And fourth, function analysis, Tata McGraw-Hill, written by Waterhooding. Thank you.